as you can see, I'm Filip Wójcik and I'm going to tell you something about machine learning. But before we start, I have to apologize you for two things. The first one is actually my voice. I spent this weekend in bed drinking hot tea and taking pills in order to cure myself from the flu. So I may sound sometimes like a Bruce Springsteen and do some funny, you know, snoozing sounds. Sorry. So you have to apologize me. And as you can see, I used to be a senior .NET developer, but dating 5 years back from today, I started to interest in machine learning and data science. And nowadays I'm working in a bank and I'm doing mostly this stuff. And today I'm going to tell you something about machine learning, what machine learning is, what machine learning isn't, and why big data and machine learning are not the same things. First of all, here is a lightsaber, cool thing. Here is the agenda, and we will start from answering the basic question, right? So first things first, what actually is a machine learning? Later on, we will move to sort of tools of the trade. So with what kind of tools and what kind of programming languages and, you know, different stuff you can actually do machine learning. Later on, I will tell you some really basics about the supervised and unsupervised learning and white box and black box methods in machine learning and data science. And later on, we will move to data structures and we will discuss in the very end in details supervised and unsupervised learning, also with some examples. So we have a lot of things to do, and I will try not to talk too much, but stay tuned for the point number 10. The most important slide will go in the end. This is the most important thing for me personally. I will try to share with you some experience that brought me up to this point. So stay tuned for the last point, let's say. Okay. As always, first things first, so what is and what is not machine learning? Here we have a simple Venn diagram, and as you can see, I have divided it into two parts. On the left one, the big circle is artificial intelligence in its, let's say, classical form. What I mean by classical form? Artificial intelligence has been here for a while. It emerged also in the mid-50s. 20th century probably, and classical artificial intelligence concentrates mostly on developing some, you know, search algorithms, game playing algorithms like, you know, chess players, A-star search, heuristics, and so on and so forth. Machine learning is a special kind of artificial intelligence because machine learning concentrates mostly on systems that can, as the name, right, suggests, can learn from experience. So you have some sort of data, you have some sort of knowledge, you are giving this knowledge to your algorithm, and it's able to draw some conclusions for the future. It's able to gather some experiences that it can use in next tasks or answer next questions that you will have for this algorithm regarding your data. So machine learning is a special kind of artificial intelligence. On the other hand, we have a big circle of big data. Big data is a buzzword nowadays. This is a, you know, keyword for corporate management and so on and so forth. And to be honest, big data is all about storage, retrieval, and processing of huge volumes of data, right? And ecosystems like Hadoop, probably you know that one, so distributed clusters and storage. It's all in this big circle. Also the very popular NoSQL movement. But there is one small problem. If you have huge volume of data, most of it probably is garbage, or at least you don't need this, right? But if you have huge volumes of data, as a human, it's very hard for you to understand and dig inside and check what actually is important. And this is the point where data mining comes into play. Data mining serves the purpose to dig inside the big volumes of data and extract what is important for you, what is important for your problem, for your business, and so on and so forth. And this point, where all of this field of knowledge meet, we used to call it data science. While machine learning concentrates mostly on algorithms, smart data processing methods. They don't need to be optimal, they don't need to be scalable. From machine learning perspective, it's important to develop algorithm that can learn. Later on, you can make it scalable. Later on, you can make it, efficient. And if you apply algorithms to real life problems, this is data science and data mining. So data mining and data science is application of machine learning to solving problems with real data. Yet another Venn diagram, let's say. This is a classical one. You can find it in almost any book, tutorial, blog, and so on and so forth. So it shows some overlapping skills that are required and come into play when we talk about machine learning or data science. On the top we have domain expertise. Domain expertise in its classical form is represented by business analysts, quants, traders, guys who are specialists in a given business, right? Here we have classical computer science, so all sorts of software developers, database developers, sysadmins, and so on and so forth. Those two groups develop data processing solutions. So all kind of applications, enterprise applications, any kind of processing, right? On the other hand, domain experts and mathematicians, but namely guys who do statistics, do a statistical research on companies' data, right? People try to find some trends in sales, people try to find some trends and approximations of client preferences, and so on and so forth. So basically this is a form of statistical research and statistical analysis of companies' data. On the other hand, mathematics, and namely statistics and computer science, meet in the field of machine learning, so developing general purpose smart algorithms, and all of them come into play in data science. So you have smart algorithms used along with statistical research for data processing, and this is data science. Okay? It's a general, let's say, overview. And here you have a short justification why is it so. What is missing on this picture are two arrows from here, and going back to the very beginning, so the symbol of, let's say, infinite loop. Volumes of data are increasing, companies are producing more and more data, and because of that we need smart methods for processing this data. But those methods need to be automated, they need to be smart. Once you develop smart processing engines, you generate more money, you solve a lot of problems, your company is growing, but you go back to the very beginning. You produce even more data than you had on the very beginning. So the circle closes and everything is running over and over again. And finally, last but not least, the distinction between those two things. In bank, when I am currently employed in, people very often put equality sign between big data and machine learning, and this is wrong. This is not the same. And what I would like you to remember after this meeting, at least one thing, is that this is definitely not the same. Big data, as I said, is about storage, retrieval, and processing in pure, let's say, technical terms, huge volumes of data. It is very much connected with infrastructure, configuration, setting up machines, setting up clusters, designing databases optimally for modeling domain, and so on and so forth. So this is big data. This is storage, right? Very sophisticated, very nice. Like Hadoop is a great technology, but this is a storage. On the other hand, machine learning is connected with smart processing methods. It's domain agnostic. You can do this with any kind of domain-specific data, medical, financial, sales, whatever, right? It's domain agnostic, it's technology agnostic. You can do this in Python, C#, Java, C++, whatever, right? And it's hardware agnostic. To be honest, to develop smart processing algorithms, you don't need clusters of, Hadoop machines or whatever. You can develop smart algorithms on small portions of data, prove that they work, that they are smart and they can learn. And later on, somebody will do for you scalable implementation in C or C++ or whatever, so it will work with terabytes of data. But at the point in which you are interested in creating smart algorithms, you are not hardware dependent, right? And well, machine learning is strongly connected with statistics, right? By definition, because it's applying smart statistical analysis to data. Okay, so once we know already what we are dealing with, we can move on to some tools, because this is always the question. In what kind of tools, what kind of tool set do we have to actually do this stuff, right? And we have several approaches, right? My personal hobby and my, let's say, research studies concentrate on developing algorithms from scratch. I'm a C# developer, so my language of preference is C# and Python, and I do this just for fun, and I do this for, you know, performing some sort of research of some small changes to existing algorithms, creating new ones. So I'm personally doing this from scratch. But for most of the time, in your job, in your work, in your company, you won't have time to develop everything from scratch. So you need to use some existing tools. And I have selected several families of software tools for doing machine learning for you. Of course, there are hundreds of libraries, hundreds of frameworks. This is just a selection, you know, of my choice. In a Q&A session, you can ask me about, you know, libraries that you were using. You can share your experience. Maybe I will be able to tell you something more about particular technology. So I have divided the technologies into several families, and we will start from big data, which is not the same as machine learning. So doing machine learning and data science on the big data environment. So we have, of course, Hadoop. And in order of appearance in time, Apache Mahout was one of the first libraries used on the Hadoop environment. It is the older one, but still it plays very nicely with Hadoop because it's built on the top of Hadoop distributed processing. So they play together very well. And right now Mahout, as far as I'm concerned, is being rewritten to new technology, so very soon we will have a new version of that one. Recently, there is a very huge hype on Spark. Spark itself is not machine learning only, but it comes with very smart libraries like MLlib, machine learning library. And in Spark, you can do a lot of statistical stuff. You can do a lot of great things regarding machine learning. So this is a very important tool. And moving to the next family, R. To be honest, there are different statistics and different surveys among people who do data science. Some statistics say that most people use R. Some statistics say that most people use Python. But those two are definitely one of the most popular, right? Either first or the second one. Software developers argue sometimes that R is not even programming language, it's a statistical tool. It can be programming language, but to be honest, R has very specific property that it's awful. It looks, at least for me, terrible, but it does the job done. So it's good in what it's doing. And one of the most popular libraries for doing machine learning in R is actually Caret. I was checking their website if they have any kind of fancy logo, but they don't have, so you have a Caret. Deal with this, sorry. Caret is a sort of wrapper. You have hundreds of libraries for R, and Caret allows you to use pretty much simple interface, let's say. Later on during this presentation, I will do almost everything in Caret in R, so you will be able to see how awful this is, but okay, it does the trick, as I said. Moving to Python, we have so-called Holy Trinity, three main libraries that are used in Python. So first one is SciPy and NumPy for scientific computations and matrix algebra. The second one is scikit-learn, especially for doing machine learning. And the last one, last but not least, is Pandas, Panda statistics, for building up the data structures used by machine learning and data science, namely data frames and also some statistical manipulations. So this is a holy trinity. If you would like to do machine learning in Python, probably you will start from that point. They have a lot of tutorials, they have a lot of materials, so it's worth checking. Last one, C++. I know that in Code Dive we have a lot of people from the C++ world. To be honest, my journey with C++ ended on the studies the second semester, so I can speak about this only theoretically. But definitely C++, okay, let me put it another way. Most of the libraries for R are written in C and C++. R is just a wrapper. The same thing goes for Python. Python libraries, the best Python libraries are actually Cython, C Python. So, okay. So probably this one will be the most efficient out of all of them. And you have several choices: machine learning pack, Shark, and dlib C++ library. I know that today we have yet another speech where the presenter will be talking about particularly this one, so I strongly encourage you to take part in that. But to be honest, this is not the end. If you are not software developers, you are business analysts, you are, I don't know, economists, or whoever else, you don't want to do any coding, okay? There are a lot of out-of-the-box tools that you can click through and you can just, you know, use as a kind of editor. I will show you today one of them, namely this one. This is machine learning library from Microsoft. The second one, probably the most popular, is Veka. It's written in Java. You can do some pure Java coding in Veka, but you don't have to. You can just use it as an editor. And to be honest, 1 week ago, me and two friends of mine from current company, we are we are competing in a challenge for data scientists. And 1 week ago, I came across this library, H2O AI, written also in Java. And to be honest, this is a very powerful, very nice tool. I just came across it 1 week ago, so this is pretty fresh stuff, at least for me, but I can strongly recommend you also that. And last but not least, widely used by economists, especially Statistica. This is a commercial software, and it comes with extension called Statistica Data Miner, and it also is especially dedicated to doing machine learning. Okay, so that's all about the tools. Probably if you will have questions regarding specific technology or whatever else, we can move on to that in Q&A session. Now, I would like to tell you something about the machine learning use cases. And we will talk a little bit on this slide, and later on I will switch to code. We have some small issues with switching between the presentation and the code, so I will first talk something. I promise not too much, and later on I will show you the examples. Sorry, in the code in R. So, first of all, we can divide machine learning into two realms. Let's say the first one is supervised learning, and the second one is unsupervised learning. And this is only one of the possible distinctions. Of course, there are many more, but in most of the books, in most of the materials, people start from distinguishing those two kinds of machine learning. And in plain words, we will go back to supervised learning later on. Supervised learning behaves similarly to school or studies. You have a set of questions, you know the answers. You are giving the example questions with example answers to your students. Students are learning, and later on you give them the final exam and you check if the answers were correct. Guys who were good can go on. Guys who were not good, you know, this is Sparta, right? And this is basically the idea of supervised learning. In unsupervised learning, as you can probably guess, you don't have set of correct answers. You can have, but usually in classical application you don't have. So you are giving data to your algorithm and you say, please find something in this data for me because I don't know what is inside. So that's it. And classical tasks assigned to both of those categories. The first one is classification. We will talk about classification in details when we go to supervised classification, namely the decision trees. So here only briefly, classification is, you know, assigning objects to specific categories, let's say, and recognizing that this is that one, and it is sometimes called an automated expert systems learning. You know, this is not the specific definition because classical expert systems were given a set of rules and they were just applying those rules statically. While classification systems, especially working on discrete data, so textual data with textual categories, discrete categories, behave similarly to automated expert systems, so they can learn rules and later on apply them one by one and assign objects to different categories. Second task, this time unsupervised, pattern recognition. Probably you know that pattern recognition in its classical form is associated with what? Face recognition, voice recognition, and so on and so forth. I will show you an example in R of completely different kind of pattern recognition. I mean the statistical data and financial or numeric trends recognition. Once we will switch to code, I will show you the example of that one. And as you can see, pattern recognition comes mostly with discovering some trends in data and also explaining that one, right? Another task, classical one, regression in supervised category. To be honest, regression is not specific to machine learning. Regression is just a statistical procedure, right? Regression is fitting a line that is approximating some trend. There are multiple kinds of regression. There is a rich regression, lasso, and so on and so forth. So under the regression hides a lot of statistical or purely mathematical knowledge, but it is very widely applied in machine learning. I will show you some trivial example in R how it behaves. But this one comes only for numeric data. Of course, you can turn sometimes discrete data into numeric one, but for most of the time, regression comes with the numeric data. And last but not least, grouping. It's assigning objects to some sort of clusters. I will show you clustering of classical data sets, iris flowers. And grouping comes with let's say, sort of supporting algorithms for many different. You can use grouping to reduce the amount of data that you process, to reduce dimensionality, reduce volumes of data, and later on apply some additional algorithms so they play nicely together. And this is a very important point. By combining, for example, grouping, pattern recognition, classification, or regression, you can discover things that are irrelevant for your data, and you can reduce the amount of data that you have. You can build, for example, decision trees, random forests, hundreds of thousands of decision trees, and you can realize at some point that if you have database with, I don't know, 20 columns, right? 20 features, you need only, I don't know, 5 or 6 of them. The rest you can take and, throw to the bin because it's useless, right? For a particular problem you are trying to solve, this data is useless. So all these tasks can play together in order to help you in dealing with big amounts of data. Okay, as promised, I will switch now to the code. I will show you some trivial and pretty simple examples. I have to turn my mic off because I need both hands, shaky hands, and yeah, but probably you can hear me, right? Okay, good. So let's move on. And okay. The reaction time of the projector is okay. And here we go. Oh, great. Yesterday in the meeting somebody called this kind of microphone Madonna style, but I won't be singing, I promise I won't be singing. Okay, let's start from the regression. And here you can see data for the cars library. This is an example library, so just for demonstration purposes. We have rows that represent cars, and we have columns that represent features. And in classical regression task, you want to find some properties or some trends that lie inside this data, and we can, for example, check that miles per gallon, how do they depend on number of cylinders in data, right? And let's check that. we should have a nice plot. Let me enlarge this a little bit. So on the x-axis you have number of cylinders in cars. In the y-axis you have miles per gallon. And of course we are humans, we are smart, or we are supposed to be smart. Not counting me, but to be honest, most of us probably see some sort of pattern here and some sort of correlation between the cylinders and miles per gallon. But machines are not yet that smart, and we need to help them in order to learn that. So we are building a very simple linear model. Linear models are, constructs from statistics, so this is pretty straightforward thing. And yeah, miles per gallon, cylinders, data, and cars. And let's do, yeah. Wow, this is pretty impressive, right? It's fitted data. The line of regression is going down as the number of cylinders grows up. Okay, this is pretty straightforward, but it gives you the impression how the regression tasks will work, right? So this is actually fitting data, fitting existing data with some sort of trends and so on, with highly dimensional data, with only number of cylinders and miles per gallon. This is straightforward, right? We have two axes, x and y. This is straightforward, but take a look at this data. How many columns do we have? Not counting miles per gallon. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is highly dimensional data. You cannot visualize it so easily, right? It will be some sort of hypercube, hyperplane, or whatever. But the idea remains the same. Even in many dimensions, data can be fitted by some hyperplane that will separate one thing from another, or that will, create some trend line in this data. So let's take a look how it looks like for the more dimensional data, right? Yeah, this is sort of prediction. We will talk about predictions later on. I will show you visualization of data separation. But we have separated 4 cars for checking if our predictions are right. So we have expected value, we have actual value, we have some differences between them, and we have fitted some simple linear model. And we can also access the residuals. Residuals, this is also a statistical term. Residuals are errors fitted in data. So most of our residuals, in this case, follow more or less normal distribution. They are centered around 0, maybe shifted to the left a little bit. But this is probably one of the ways that you can visualize quality of your fit for multidimensional data. Here you can see the residuals plot. Points represent the expected values, line represents the fitting value in 2 dimensions, and for multidimensional data you come with a lot of different plots, like for example normalized residuals, so depicting the multidimensional data in 2 dimensions, and you can see how your residuals, so error of your prediction, are distributed. And yeah, more plots for accessing this kind of prediction. So this is regression. It's purely statistical, purely mathematical. I will show you right now how clusterization looks. Right? We have a classical, yet again, classical iris data. If you were doing any kind of machine learning, you were interested in this topic, probably you came across this one. It's especially used for neural networks. I don't know why 99% of tutorials about neural networks start from iris-setosa classification. You have different kinds of iris flowers. They have, different sepal length, sepal width, petal length, petal width, and you have different species, right? And you try to classify new iris flower basing on the properties of its, sepal length, sepal width, and so on and so forth. It is, for most of the time, it is used for the classification, but we will do a different task. We will try to do clusterization. And here it goes. Clusterization is this. Every point here represents a row. Numbers are row IDs, let's say, a sort of, from database word, it will be a kind of kind of primary key, right? So every row, every object has its unique identifier, and clustering algorithms can group similar objects together and form, some sort of explanation and exploratory data analysis for you. So you can see that algorithm created, definitely group number 1 is separate from the others, and here we have we see that in group number 3, group number 2 overlaps, so there is no clear distinction between them. So this area is definitely problematic, but it gives you the impression about how your data looks like. Yet another example. As I said, pattern recognition. We have in here data regarding the number of passengers using planes in time. On the x-axis you have years, on the y-axis you have number of passengers in thousands and hundreds of thousands, and you can see how it goes along the years as the time passes, right? And pattern recognition not only applies to face recognition, voice recognition. You can try to approximate the time series analysis, how this trend will go in the future, and this is how it looks like. You can do the following. I suffer from color blindness, so sorry, I guess that this line has a slightly different color than that one. For me it looks gray, for you probably it looks in some different way. But definitely this line, this different line, means the approximation of the trend, how it will go. The dotted line above and below, probably it also has some sort of different color. These are lines showing confidence interval in terms of pure statistics, right? So how our approximation can go bad in plus and in minus. So this is the margin of error that you are making, right, in your prediction. But this is kind of pattern recognition. And, not always and not only face recognition or voice recognition. This is not all. Okay. This was short, let's say, code part. We will now move on to the next stuff, and we will go back to the code later on. Next thing, and next very important distinction, especially in business, in practical applications, is to black box and white box methods. This is not obvious because in technical terms, if you are software developers, you don't care if you write from scratch code for neural network or decision tree, okay? You just write code, you do some fancy, very nice stuff. But for the business guys, this is the crucial distinction. Currently I'm working in a bank, and in bank people prefer white box methods because of transparency and explainability. They do not like to go into black box methods because, this is not good to say that, the prediction of neural network was that sales will drop by 300,000 Swiss francs this year. Why? Because the weights in the second layer were between minus 1.3 until 2.33. Okay, but what does it mean, right? It means nothing for somebody who is not technical. So, as you can suspect, black box methods are machine learning methods, mostly very engaged and deeply connected with some statistics, mathematics, that use some mathematical properties that can be easily visualized and interpreted by humans. On the other hand, white box methods are methods like rule-based systems, decision trees, clusterings, what else? Any sort of association minors that can be interpreted directly by humans. And if you work in a company or if you are doing stuff that requires explainability and human friendliness, you will probably go for the white box methods. If you require higher accuracy of predictions, probably you will go for black box methods, but you will lose the connection of interpretation by human beings. For most of the time, not always, but for most of the time, black box methods are more accurate than white box methods. Why is it so? One of the reasons, of course, one of the many reasons, is that black box methods operates on some mathematical data shifting, like using kernels, putting data into different dimensionality, adding quadratic terms, and so on and so forth. So doing mathematical operations on data that reshape data into a form that is almost not recognizable from the original. And that's the reason why you cannot interpret this, but there are maybe some mathematical properties that make the data more explainable, and that's the reason why those algorithms are more accurate. Not always, but very often. But in the same time, white box methods operate on the data almost unchanged from the original, and that's the reason why they cannot generalize, or they cannot find so sophisticated correlations and some mathematical properties inside, and that's one of the reasons why black box methods are more accurate than the white box ones. Okay, quick talk about key data structures. You have seen previously the, let's say, data frames or something similar to tables, but in general we can say that this one will be, this one will be shocker. You'll be shocked by this slide. I suppose that data can be structured or unstructured. This is shocker. Nobody expected that, I suppose. And structured data, in most of the time, comes in an SQL-like style, or flat files or logs. But SQL-like style, so tables, came in the form of data frames. In almost every technology, Python, R, VK, Machine Learning Studio, whatever, it is called data frames. It looks similarly to SQL tables, right? Every row represents object, every column represents feature or dimension. We call this differently, but we operate on stuff like that. Unstructured data, for most of the time, not always, is connected with text data, so natural language processing, or data that you need to clean by yourself. You can have a text data, but you can discretize it. You can cut into different bins, divide into categories, and build up some sort of tables out of this. So most of the time, text data is used for natural language processing, and we also have a sort of semantic networks. There are very sophisticated tools for parsing the web and dealing with natural language, but this is kind of different story. And we will not stop for long in here because you have already seen the code. Yeah, not much to add. We have tables like SQL, and we have different kind of features. The most obvious ones are discrete features, sometimes called categorical features. So features that have a finite number of possible values. Most of the time textual ones, but not always. But for most of the time, textual columns are discrete features. Like in financial instruments, you have equities, bonds, structure hybrids, forex trades, and so on and so forth. Probably 15 unique values will be in here. So select distinct financial instruments from table will give you all possible so-called levels of factors, right? So finite value set. Other features, of course, Boolean ones and numerical features. This is pretty obvious. And records objects are representing every row is representing objects. So pretty much like in database or data processing world, let's say. We have also different kind of features. We have features that are ordinal. So, for example, time series data. Dates that came before are before, dates that came after, right? So, any kind of correlations between data can be captured by the data frames, but the structure looks more or less like this. Another important property of data frames and many machine learning algorithms is that there are very fancy algorithms, very smart methods, but there is little trick. If you have data like this, and you have very fancy algorithm, which can work only with numerical data, so you have a problem, right? You have columns with text, you have some discrete values, so how to turn them into numbers? Actually, you can do this without any problem. We are doing so-called one-hot encoding. On this picture, this is not let's say fully correctly depicted because, for example, you have 3 possible values in the company column. So you encode this on 3 bits, but it will create 3 distinct columns. I have created this in the following way, as you can see, to be, the slide is not too cluttered, but it will be company X, company Y, company Z. There will be 3 columns, and 001, 010, 100, and so on and so forth. But basically, you don't lose any kind of information by doing that sort of transformation in data. You can train decision tree with textual data, and you can transform data into this form, train neural network, and you will get very accurate predictions. No problem at all that you changed companies into several bits, and you are encoding this in many different columns. No problem, no problem. So that's a short digression about data structures, and probably the most scaring slide in this presentation. This is a subset, only a subset. There are hundreds of algorithms, so don't treat this as, any kind of thing written in stone. This is just a subset that I have selected for you. We have supervised, unsupervised, and slowly dying learning expert systems. Supervised learning algorithms can be divided into categories I was talking about earlier. So we have regression, linear, adjusted, restricted, and so on and so forth. We have decision trees, discrete and regression trees, also sometimes called model trees. We have rule-based systems, which are somehow similar to decision trees because every decision tree can be represented as the rule-based system. Not the other way, there is no direct conversion without some adjustments. Of course, we have neural networks. This is a huge family. There are neural networks like feed-forward perceptrons, there are self-organizing maps, coherent networks, and so on and so forth. So this one is a huge family. There are, of course, optimization algorithms sometimes used to train neural networks. They help to train neural networks, or they help to tune any other algorithms. And unsupervised learning algorithms like correlation finders, clustering algorithms, and my favorite ones, association miners. I'm trying in my research write algorithms that combine association mining with decision trees and classification. And a sort of learning expert systems, which are expert systems connected with fuzzy logic, probabilistic expert systems. But for most of the time, you can create decision trees with learning probabilities of occurrence of given event, and you will get more or less the same thing as probabilistic expert systems, right? Okay. Right now, I would like to focus on one particular type of learning. Of course, there are plenty of them, and we are talking about only small subsets. But we are limited by time, and we have to deal with that. What I would like to show you right now is one particular subset of machine learning, which is supervised learning, and namely classification. Yet again, I will be talking for a while, and later on I will show you some code and something that, some action, let's say. The basic idea with supervised learning is that you have 2 data sets, like on a university. One is for training, one is for testing, and you give to your students example questions, example answers, they study, later on they go to the final test, you give them final questions, and you grade them. You have a teacher or oracle that is giving grades, and for most of the time this is some kind of objective rating function. We have different kind of functions for different tasks. If you are doing classification, you go for some, indicator loss functions, precision, recall, true positive rate. If you are doing regression, you have mean squared loss, and so on and so forth. But believe there are many different functions that can do the trick. They can be either objective and general, or they can be specific to a given task or problem, so a lot of things to choose from. And algorithms learning from experience. On the next slide, you will see a short diagram presenting how the algorithms are learning, right? And this is one of the most important things in supervised learning. Sometimes there is a case that you are trying to predict, or you are trying to solve a problem for which you have very limited amount of data. For example, in medical domain, maybe you are trying to build a system that will recognize a particular kind of cancer, given the symptoms, but you have very few patients who suffer from this disease. And you need to spare your data, you need to use it wisely. And that's the reason this is one of the key factors, and this is one of the key points that needs to be done before doing any supervised learning. You need to partition your data into two sets, training and testing. Here is an example of a rule of thumb. In most of the books and resources, the suggested distinction is 70% to 30, but this is just a rule of thumb. Right now we are competing in a competition or challenge where we are dividing into 95% to training and 5% testing. Just, you know, depends on the specific occasion and problem. And why is it so? This thing is very simple. If you have very limited amount of patients suffering from a given disease, you don't have enough data to, if you give everything to your algorithm, you won't be able to check if it's learning correctly and if it's improving, right? You need to save something for yourself for the final exam, right? For the students, let's say. And maybe I will be able to switch. No, I'm not. Okay. So we will discuss one more slide, and I will show you the code because we need to switch the screens. Here is the overview how the algorithm proceeds. You present training data without the answers. Algorithm is learning, it's updating its internal memory, and it's trying to predict the answers. You are, you know, punishing it for the bad answers and prize for the good one. You calculate any kind of error rate you are using, and algorithm is updating its internal memory, it's updating the internal state of knowledge, and you start yet again iteration on some other set of testing questions, and so on and so forth. You continue up to the point when you realize that the error is low enough, or you select any other kind of criterion to stop learning, and you do final test. Pretty simple, right? And I would like to show you supervised learning with decision trees, and one more slide of talking and we switch to code. So general approach for decision trees is that they operate most of the time on structured data, so those data frames, SQLite tables. And they apply recursive top-down strategy, classical one known from computer science named divide and conquer. They try to divide data into subsets on the attributes or values that reduce the amount of error or impurity or variance, depends on what kind of data do you have. It can handle both numerical and discrete data without a problem, or you can shift from one to another. Decision trees, single decision trees are very flexible. They can represent a lot of problems, and they're quite easy to implement, and what is more important, they are easy to interpret by humans. I talk about single decision tree. Decision trees can be translated to human-readable decision rules, and this is also cool because you can print it in the form of report, you can show it to people who are not technical, and so on and so forth. Of course, single decision tree is cool, but it's even better to have hundreds of decision trees, and this leads to very powerful algorithms called random forests. But we have to, you know, limit ourselves to some subset of topics, but maybe next year we will meet again and I will tell you something about random forests. But the funny thing is that while simple one decision tree can be interpreted by human, if you create random forest out of boosted data, resampled data, and so on and so forth, random forest, so forest of many decision trees, cannot be interpreted by human. This is also a black box because there are hundreds of decision trees, and all you can get out from it is some estimation of variable importances or some, you know, descriptive statistics of the models. So many decision trees are not so easy to interpret. Okay, let me switch now. Let me switch now to the code, and I will show you several things. Okay. We have to wait for the, as always, for the reaction time. First of all, I will switch to the Microsoft Machine Learning Studio. This is a tool hosted on Microsoft Azure. I can show you how the splitting of data works in R, but as I said, R is awful, and probably if you don't know R, it will mean nothing to you. So, okay, this is a function that splits data into train and test. Cool, great. But, you know, one picture says more than 1,000 of words, so yeah. I have an example of Titanic survivors data. This is a classical one. This is example from Kaggle website. So, you know, we had a famous, very well-known tragedy of Titanic ship. And we have a data of people who survived or not survived Titanic disaster. This one I can show you in R, I guess. Yeah. Every row represents a person, and we have a columns like age of the person, embarking information, fare that was paid. This is the number of parents that were present on the ship, passenger class, sex, number of siblings or spouses, information that is most important for us, so if the person survived or not, if the person has a family or not. You can see some redundancy in here. Why do we need information if the person had family or not, if we have a number of siblings and spouses or parents? But sometimes it's better for algorithm to have several columns that are duplicating, sort of redundancy, because it will be easier for him to pick up some, you know, some correlations and some trends in data. So it's very often used technique that you approach the same problem from different directions. Okay, you have number of siblings and spouses, you have number of parents, but let's put some Boolean feature, yes or no, if a person has a family. Maybe it will help decision tree to establish some meaningful rules, right? And so on, family size, title, deck on which person was embarked. Sometimes the information is unknown. And we have a fare per person, so we have information about how much the guy paid for the family member. And right now we are switching to completely different technology, Microsoft Azure, so cloud service, and this is intended mostly for people who are not software developers. You just drag and drop some boxes, and we have the same data, so Titanic survivors data. It will be depicted in a little bit different form in here, but you have different columns, and you can check, for example, the purely statistical information like histograms of distribution of, for example, passenger classes. We can see that for most of the time we have passengers of class number 3, most of them, and so on and so forth. So basically the same thing as in R. And we do data splitting. So we split our data set into two, training and testing, as I said. And this is randomized split, and we take 70% of data to training and 30% to testing. And we can do the following. We can do, for classification, keep going, no. You don't want to cooperate, as I see. Okay, keep going, keep going, keep going. Where is it? Initialize model, classification. And let's say we are doing two-class decision forest. One of the possible options, right? So we will have hundreds of decision trees that will be learning from data. As I said, one decision tree is cool, but several decision trees are even better. And you can do the following. Train model. You take 70% of data for training. You train your model. We select properties like, for example, we will use 500 decision trees. Sorry. Maximal depth of tree, let's say it should be about 15, 20 will be too much. And you can set different properties for different algorithms. There are some heuristics that come with, let's say, experience with dealing with the different algorithms. And you say what is going to be predicted. So survived survival rates of if the person survived or not. So this is the one, and our model will be trained, right? And for the final stage, once the model is trained, you can evaluate your model on sorry, not evaluate, but score. This is I don't know why they call this in this tool. They call this score model. Usually in literature and tutorials, it's called actually evaluating, but whatever. You need to give scores to your students, right? You have a trained model, and you need to check how it's behaving and if it's getting good scores. Here you have test data, so 30%. You give it to scoring, and the model actually will be scored, and you will check how well it's doing. And later on, in the end, we will have some evaluation metric, like, for example, what was the final grade. It will take some time to evaluate, let it be so. In the same time, while that one will be calculating, I will show you a single decision tree. I will show you a single decision tree, and it will be created in R. So here we have one. This is epic. To be honest, I have never seen this picture in that scale, and it looks epic. So you start from the first node, and decision tree has decided to divide passengers by their title. So people with title of Mr. go to the right. People with title of Master, Mrs., Miss, and some others go to the left. Let's concentrate on Mr. because this is easier one. If the guy was on deck B, C, D, or E, you have this proportion of guys who survived to those who died, right? This is pretty much 34% of people survived, and the rest died in catastrophe. And on the other hand, if the guy was on deck A, F, T, or unknown, most of them died. And this is a single decision tree, which is pretty easy to understand. And as you can see, you can turn the path from a given starting node. So if you start in here, you go one by one, you form a sort of decision rules, right? If the title is Master and deck is B, C, or D, then you have 33% that you will survive. If you are Master, Mrs., Miss, or other, and your class is bigger than 2, and you have paid less than 23 and 25 per person, then you are probably above 62 or 63% to survive. This is a kind of decision tree. This is a kind of set of decision rules that, as you can see, can be presented in the form of a picture or translated to rules that are written in plain language. And let's check the... Okay, this is done. So we had a random forest of many decision trees. We have checked on randomly selected test data how the model is doing. And for most of the time, in Java, Python, C#, whatever else, you have different scoring metrics. And for classification problems, we are talking only about classification, okay? The most important probably for you will be accuracy. Accuracy is the measure of correct hits. There should be that person survived. Algorithm predicted that the person will survive. Okay, that's 1 point. And so on and so forth. So this is the percentage of correct predictions. There are many, many more, like true positive rate, false positive rate, precision recall, and so on and so forth, lift. There are many, many scores for evaluating algorithms, sometimes very sophisticated, and you need to choose the proper statistic for evaluating your model, depending on task you are doing, and you observe, for example, tuning different parameters of statistical models result in different predictions. So not always you need to push onto correct accuracy. Sometimes it's more important to concentrate on, for example, false positive rate. Because if cost of misclassification is too high, it won't be good. Okay, you will receive the presentation in the written form. So I have created for you, static presentation how decision tree works, I suppose that we don't have to concentrate on the static pictures because we have a code. And so, as a sort of summary for decision trees learning, we can say that decision trees are best used for classification and regression tasks in the form of decision forests, so many decision trees which are more accurate. Also, decision trees are good in explaining complicated data. I will switch back to the code when we talk about association minors. I forgot to show you one important plot, which is variable importance. If you have 100 of decision trees and none of them used attribute, for example, I don't know, sibling and spouse count, it means that this attribute is irrelevant for prediction. I will show you the plot. Sorry for that, I just switched too quickly. So it is a sort of explainability. It's giving you hints about your data and detecting irrelevant features. And also, profiling clients, profiling any kind of associations or important rules that are in your data, visualization as a side task or side node, and building rule-based systems, because they can be translated, decision trees can be translated to rule-based systems. So that's it for supervised classification. We are near to the end. And short side note on unsupervised learning. So as I said before, the idea is that you have, for most of the time, one data set, you don't have a correct answers, or you just don't show it explicitly. And there's no teacher or no oracle, so nobody is saying for algorithm that you made 5 mistakes, 6 mistakes, or whatever. Algorithm is deciding on its own, and you just check if it makes sense. There are some internal measures for example, clusters quality, like internal variance inside the cluster, intra-cluster variance. So, for example, if points assigned to different clusters are not too similar, maybe we can merge those two clusters together, right? And one of the tasks of unsupervised learning is mining association rules. And as I said, as a part of my research work, I try to investigate how much we can apply association analysis into classification, and maybe it will give us some better results. And yet again, we switch to the code, and I will show you classical, very short example of so-called market basket analysis. But before that, I promised you to show the variable importance plot out of the random forest. So let's do this quickly. And as you can see, this is the one. Here we have attributes from Titanic data, and on the x-axis we have the mean decrease in Gini factor. Gini factor is a factor of impurity in classes of your data. So as you can see, the attribute of title was most important one in all decision trees coming into the random forest. And for example, attribute has family was least important. So probably you can skip that one and spare some memory, spare some processor cycles and so on and so forth. So you can skip that one, probably that one too, and take into account only the most important ones. Okay. So this is a variable importance plot which comes from decision trees. And okay, let me show you the market basket analysis. This is pretty much interesting topic. Yeah. Here we have this one. Here we have probably you are running some sort of shop, and you are checking what people are putting into basket together and going to pay for it. And probably this is some sort of vegetarian shop, because I can see a lot of soya, walnuts, and salads. So whatever, right? This is a trivial example. You would like to create a discount that will give you the most, profit, the biggest profit. So you would like to check how often people buy several goods together in order to make a targeted discount. So for example, if you buy soya and salad, you will get a discount because many people are buying that, right? And you can see this here. we have a sort of frequent items. Frequent items mining is pretty much important in data discovery and learning from data. So you check which items occur quite often. So you can see that soya in your shop is about 30% of transactions. Support is a measure of actually probability. If you have a number of transactions, how many of them contain this item? They don't sum up to 100 because you are counting every kind of item separately, right? So this is frequent items mining. This is a purely statistical operation, but you can also do much more fancy stuff like checking the rules. So, for example, you can check how often, and we have several measures for doing this. For example, people are buying salads and walnuts and bread. So support of the rules, so number of transactions in which they occur is about 20%. But confidence is a measure how often the consequence of the rule, so buying bread, occurs when the hypothesis of the rule occurred. Hypothesis is the left hand of the rule, so the condition. You can read this one as if. If you buy salad and walnuts, then you will buy bread. And in this transaction set, it's about close to 100%. So you can access those rules, and you can also plot them. You can show them in stuff like that. If you have more rules, it's getting more and more cluttered. I made a small research, and I guess that all elements on this picture are in shades of gray, so there are no colors here, I guess. Excuse me? 50 shades of gray, yeah. So you can see associations between different elements, and the bigger the circle is, the bigger support is, so the bigger probability of the elements occurring together. And the darker color is, the bigger is lift. Lift is a measure of also percentage of, let's say, dependence. And we can, and this is what I'm actually researching, is it possible to use that kind of rules to generate some sort of predictions, not only to explain data, but also generate some sort of predictions? I believe that it's possible. But this is one element of research. There are many different algorithms and many different ways of applying this to in practice. Also, you have in offline version of presentation, you have a small example, basically of the same shop, probably vegetarian one. How is it working? And once you will get the presentation materials, you can check this on your own. So this is how it looks like. Some associations, right? Okay. So what is unsupervised association learning useful for? Anomaly detection. In its classical form, anomaly detection is done by using the normal distribution and checking points that are on the bell curve far away from the center. But you can use association analysis to also find some anomalous elements that have too high probability of occurrence than they should. You can, of course, this is obvious, search for correlation and do some data explanation, right? If you can, this is white box method, you can plot directly the rules that you have created. And we can say that this is a kind of pattern recognition. There are also algorithms for detecting irrelevant features using the association mining and association analysis. So this is also one of the possible applications. Okay. And finally, we get to the point that I will shortly stop talking, and probably the next slide will be the most, I believe, and I hope that it will be one of the most important ones for you. When I was starting to dig in this topic, it was about 5 or 6 years ago, I started from the bad direction. I started from this one, and please don't do that. If you don't know anything about machine learning, maybe after this presentation you would like to start digging deeper into this topic, don't start from this point. Don't do this. Start from that point. And I can suggest you some lectures. This is a brilliant book that gives you practical examples in Python. The book assumes that you will create from scratch implementation of, for example, decision trees, rule-based systems, clusterings, and so on. The book is written in Python, but you know, Python is very universal language. If you are C#, Java guys, or JavaScript guys, or whatever, you will have some fun translating Python to your favorite language, but the book is very practical, so I hope that you will enjoy it. Moving on the scale to more theoretical one, Collective Intelligence, the title is misleading. This is book just about machine learning. It has nothing to do with social networks. I don't know, when I first saw this book, I was thinking that it's about social networks, so I just threw it away. But this is a very, very good book. I see it as sort of continuation of machine learning in action. Very good book, and also written in Python. It gives some more details about algorithms that were briefly presented here, and it also gives you some more algorithms that were not presented here. If you still want to investigate the topic, you can move on to this position. This is old edition. There is a new one, and this book is a little heavier in theory and maths. It also goes very deep in the topic of self-organizing maps and multi-layer perceptrons, so neural networks, one of the kind. And this is the book I have started with, and it was a bad choice for the beginning. This is a brilliant book. I don't want to say that it's bad. This is a brilliant book, but it's very heavy on math and theory. If you begin with the topic, probably you will feel a little bit overwhelmed. It's also using R, which is awful in my opinion. And if you would like to start with machine learning and you start with R, if you are not a passionate, you will, give up quickly, my opinion. So don't do this way, from right to left. If you would like to, and you want to do this from left to right, that will be a preferable option and preferable choice, I think. If I can advise you something, it will be that one. Okay, so that's the point when I stop talking, finally. And thank you very much. I guess that we will have now a Q&A session, so please ask questions.